Welcome back, everybody. I'm Ryan Tiptrani. I'm a faculty at CMU. I'll be the moderator for this session. I am very pleased to introduce Andrea Montanari for the first talk, for the invited talk of this session. Andrea is a professor at Stanford University in electrical engineering and in statistics. And Andrea is well known for his great work for many years on a variety of topics, and has recently become one of the real thought leaders in the theory of overparameterized machine learning, always doing something new and exciting. So I'm very interested to hear his talk on projection pursuit to interpolation in small neural networks.
Thanks, Ryan, for the introduction. Thanks to everybody for organizing this and inviting me. So I'm gonna report on some recent work, and all the newish stuff that I'll talk about is joint work with Chao Zhang, who is a postdoc moving to Wisconsin next year, my group, and Kanje Zhou, who is a student in the statistics department. So I want to start. I spend perhaps 10 minutes or so trying to take a broad view of what has been achieved so far within the context of overparameterized learning, of the theory of overparameterized learning, and what I think are the goals here. So to set the stage, what I'll talk about is binary classification, so the standard model in which we have IID data from some common distribution where the xi are feature vectors in RD and the yi are labels that I'll take to be binary. Of course, I want a model that is a function from RD to R, and what I look at in this talk is minimizing a loss of this form typically, so classification loss in which I try to achieve a margin kappa. Okay, so all the examples, or most of the examples, nearly all the examples that I look at, the loss is positive if the argument is less than kappa, if the margin is less than kappa, and is 0 if so L of x is 0 if x is bigger or equal than kappa. Okay, so you can think of, it doesn't really matter as you will see, but you can think, for instance, of hinge loss. Okay, and this is applied to the argument that is yi times f hat. And okay, what we have in mind is of course that we are in overparameterized regime, so there are perfect classifier, there are solutions that achieves this margin kappa, and we'll try to find one of them via, for instance, gradient descent. And by the way, feel free to interrupt me if you have any question. No. Okay, so this is the broad context in which we want to work, and the question in this area is why does this work? And somehow the intuitive picture that has emerged over the last few years is the following: that in an overparameterized model, you have a space of possible models. Models are indexed by a parameter vector theta. This can be the weights of your neural networks. So P is the number of parameters in my network, and there is a set of empirical risk minimizer for any margin kappa, that is the set of parameters theta that achieves margin kappa when you use them in the model F, okay, on all the training sample. So this set is non-empty and is potentially very large, and you start gradient descent in this empirical risk at some point in which the loss is non-zero. So at this initialization, perhaps R hat is strictly positive, but since the model is so overparameterized, there are many empirical risk minimizer, and gradient descent quickly converges to an empirical risk minimizer that is very close to the initialization. So here overparameterization, of course, plays two roles. One role is that it simplifies the optimization, in that the intuition or the hand-waving argument is that if you have a lot of parameters or many more parameters than inequalities, then it's easy to satisfy all the inequalities. And the second role is that, of course, when the model is very overparameterized, you need to move very little from the initialization. And because of that, somehow the model that you come up with is simple, is not complex, because you spend very little time training it. Okay, so this is the hand wavy picture, and if you want to break down the question of why does this work, I can think of three types of questions. The first question is a structural question, and is, when is it true that the set of empirical risk minimizers is non-zero? Okay, under which conditions, for which sample size is it true that there are perfect interpolators? I use here the word interpolator to mean any model that achieve kappa margin on all the samples. Second question is the optimization question. Can we find one point in this set efficiently? And in particular, does this become easier in some sense computationally if the model is overparameterized? And question number three is the statistics question, has to do with this complexity argument that I gave, that is, the model that are reached by gradient descent are simpler. So you want to answer the question of what is the bias, the inductive bias induced by gradient descent, and why is this possible? Is it possible that this is sufficient to regularize the model? After all, this is a very minimal bias, because you still go to interpolation, you train the model to interpolation. How is this possible that this is sufficient to regularize the model? All right, so this is the three broad question. It's fair to say that by now there is one case that we understand well, and this is the convex case. So what I mean by convex case, I mean that the function is, theta. So there is a featurization maps phi of x that takes the input data and spits a vector of length rp. So phi goes from rd to rp. And there are p parameters, and so you take a linear combination of these features. Okay, and this feature map is not trained on the data, is independent of the data, and then you fit the theta, the parameter theta, by minimizing a convex loss. Okay, so this model, as simple as it is, cover a lot of interesting cases. So let's quickly go over them. It covers kernel ridge regression. In this case, in the case of kernel ridge regression, this is really a map from RD to a certain Hilbert space, reproducing kernel Hilbert space. It covers random feature models, that is Al-Arami rect, that is two layers neural network in which the first layer is random. In this case, the ith component of phi is just a nonlinear activation applied to wi times x, where wi is fixed, random, and independent of the data. It covers neural tangent models. In this case, phi of x is the gradient of some neural network, say f with respect to theta at the initialization, okay, where this is perhaps a neural net. And it covers, of course, a number of losses, for instance, logistics, square loss, etc. Okay, so this case is simple but interesting. And I would contend that more or less we know the answer to all of these questions for this model. I mean, we can keep studying it. It's very interesting model, but we know all of the answers, roughly speaking. When is the ERM non-zero? Well, this depends whether you are looking for interpolation in the sense of square loss of regression or in the sense of classification. For regression, it's very simple. Under some genericity condition, you need the number of parameters of a number of samples bigger than one. If you look at classification, there is typically a threshold that depends on kappa that we can compute using known tools, and above this threshold there exists an interpolator. Can we find it efficiently? Yes, because, okay, these are convex problems, so we can find them efficiently. Does overparameterization help? Well, this is a model in which this question is not particularly interesting because it's always easy. It's always polynomial time to find an interpolator. What is the bias of gradient descent? This is, the answer is simple, but still interesting. In this case, if you run gradient descent of gradient flow, for instance, in the L2 loss, the point that you converge to is the argmean of the L2 norm of theta. And the same for logistic loss. You look at the you converge to max margin classifier, which corresponds to minimizing the L2 norm. So at least for gradient flow is very easy, and the bias is or gradient descent, and the bias is the L2 norm. And finally, I think I find the most surprising or interesting part of this model is, we can understand quite precisely why this very simple bias that is minimized the L2 norm among regularization among the interpolator is sufficient to regularize the model. And the reason has to do with the nonlinearity of the features and to the presence of a lot of effective noise that acts as junk features. And these are equivalent to adding an extra to regularization. So even putting, minimal regularization that is minimized the L2 norm among the interpolator is sufficient is optimal in some cases. Okay, so there are lots of papers on this. Of course, I'll showcase this with 3 plots or 4 plots from my papers of my groups. This is a paper a couple of years ago with Song Mei, in which we computed the double descent curve for a random feature model at square loss. And so we can reproduce the whole phenomenology, completely analytically of the double descent curve. This is a paper with Yichao Zhang, in which we looked at the neural tangent model for 2 layers neural network, so a more complicated model. And here what we plot is, so this is the test error in all of this plot. This is the test error, and here we plot the test error in the plane of basically number of parameters on the x-axis and number of samples on the y-axis, and each slice along this plot is a double descent curve in which the risk goes up and then goes down. And the main result in that paper is that if basically the number of parameters, p over n, is bigger than 1, bigger than big constant, then basically the risk of the neural tangent model is similar to the risk of the neural tangent kernel. Okay, so this is the infinite width limit. So this is kind of clarify why growing the number of parameters below the interpolation threshold doesn't hurt, because you converge to this RKHS risk. And finally, this is a paper, an example in linear models in which we derive the exact curve for max margin classifier. And again, here the interpolation threshold is not 1. This is again p over n, but still you see the descent after the interpolation threshold. Okay, and okay, so this is just an example of 3 examples of a very long sequence of papers that didn't start with us. And here are a few of them. And all of them are about linear models and convex loss, Bartlett et al. And they studied the ridge regression and the idea of benign overfitting. Racklin and co-author that studied kernel ridge regression and many others. And okay, on purpose I omitted work by speakers in this conference, for instance, Lenka, Jeff Pennington, Edgar, and many others that worked on this. Okay, so there is a big hole here missing that we know how to understand. We know something about convex models, know a lot by now about convex models. What about non-convex models? And if I go through my list of questions, we don't know how to answer any of them really in a rigorous way, at least as far as I can see. So this talk will focus on the first question, that is try to develop tool to understand when is it true that the set is non-empty. I think this is, if you don't know how to do that, you will not know how to answer the others. And I think any insight in the technique to answer this question will have a positive effect. So the plan of the rest of the talk is as follows. I'll first go over a toy model that is this negative perceptron model that is really the simplest non-convex model that I can think of, and describe a little bit some results and some phenomenology there. And then, take a detour and revisit an old problem that is projection pursuit, and describe the connection to neural networks, to two layers neural networks, small two layers neural networks, and describe a generalization of projection pursuit. And the negative perceptron in this paper and the projection pursuit is in this paper that hopefully we'll put on the archive soon. Any question? Okay, if not, I'll start. Okay, the negative perceptron. So what is this? Again, data are xi, yi, the yi are plus minus 1. And we look for a kappa margin classifier where my parameter vector is on the unit sphere. I will constrain it to be on the unit sphere. There is not really loss of generality in that. And the loss, you can think of any loss that is again, for instance, hinge loss. Doesn't matter because in the end I look at zero risk. So the set of empirical risk minimizer is a subset of the unit sphere. This is the unit sphere that satisfy all of this linear inequality. And now why it's negative? Because I'll do the funny thing of taking kappa negative. Okay. So it's different from what we do normally in machine learning or statistics. Perhaps it's less justified from a statistics or a machine learning point of view, but mathematically is perfectly well defined, and it's interesting. All right, it's interesting because the geometry is more interesting than in the convex case. And what is the geometry? The set of empirical risk minimizer is the set of vectors of norm 1 that satisfies a set of linear constraints. Remember that the constraints are yi, xi, theta bigger or equal than kappa. So if I call zi to be a yi times xi, you can write each constraint as a half space constraint. And the half space is a half space that contains the origin. Okay, so one of these constraints here is represented by these red lines, right? And the shaded region is the region that is forbidden. Okay, so the region that is allowed is the white one. And you have to intersect this with the sphere. Okay, so as you see already in this example, you get a non-convex set. In general, okay, I'm not good at doing drawing in D dimension, but in general, the picture is that you have the sphere in D dimension, and then you are carving out spherical caps from the sphere. So you are digging holes in the sphere, and what in the sphere, yeah, and what you get is spherical Gruyere. And so the set of empirical risk minimizer is this ugly or this beautiful spherical Gruyere. Okay, just to emphasize, this is very different from what happens in the case of kappa positive. In kappa positive, the usual case, we have, of course, a set of half spaces, but the half spaces don't contain the origin. Okay, so they are like this. And you want to intersect with the sphere. Okay, now this is an ugly sphere for sure. But you want to intersect them with the sphere. And you can see from this ugly picture that the intersection is non-empty if and only if the intersection with the unit ball is non-empty. Okay, so the intersection with sphere is this, and the intersection with the ball is this. So if the intersection with the ball is non-empty, then then the intersection with the sphere is non-empty. You can always rescale vector, and this is a convex set. So per se, the set of empirical risk minimizer is not convex because still lives on the sphere if I constraint, but finding a point is equivalent to find a point in a convex set. So the geometry is very different. Okay, so perhaps I should stop and ask if there is any question about this model. Okay, if not, okay, the question that we want to answer is when the empirical set of empirical risk minimizer is non-empty, and when can we find a point there efficiently, right? Now, question 2 that before was trivial now becomes entirely non-trivial. And question 1, the techniques that we had before, or we used them before, do not really apply as such. Okay, so to state results for question 1, let me define a threshold. I look throughout the talk at the case in which the number of samples over the dimension. I always look at cases in which the number of parameters is proportional to the dimension, right? And in fact, in this case, P is equal to D, right? And I look at cases in which the number of samples divided by the dimension, so this is basically asymptotically equivalent to the overparameterization or underparameterization ratio, converges to a fixed number delta in 0 infinity. This is somehow the critical regime, the most interesting regime. Okay, so look at this limit and then ask yourself, is the probability that this set is non-empty in the limit bounded away from 0? And I call the largest delta such that this happens. Of course, this probability decreases with n. Because you'll have less and less, more and more constraint. And so I look at the largest delta such that this is bounded away from 0. This is the interpolation threshold, my definition of the interpolation threshold. Okay, so this problem, in fact, as a history, the case kappa positive, the convex case, if you want longer history, the oldest paper that looked at, a threshold phenomenon for this is cover 65 that looked at the case kappa equals 0. So whenever intersection of half spaces is non-empty, and it showed that you need 2 half spaces, you can have as many as 2 half spaces per dimension. For kappa positive, so this is the xi, there is not really model on the xi. The xi can be in generic positions. Elizabeth Gardner 88 used the replica methods, so physics methods to solve the kappa positive, to give the threshold for kappa positive when the data are Gaussian and the label are random. Very, very nice paper. And this result was proved by Shrebina and Tirozzi in 2003, and then Stojnic gave a very elegant proof using Gordon inequality. So all of these are for this pure noise model. The case of model noise that is not, labels that are correlated with the features, and, a number of other results were in this paper of Candes and Sur. And, here they assumed logit, and here they also derived the, asymptotics of the empirical risk minimizer below the interpolation threshold. And in this paper, we looked at general function, link function phi, and we derived, properties of the max margin above the interpolation. So all of this is kappa positive. So as I said, it's fair to say that is well understood. Kappa negative, I know all your results for pure noise. A formula for delta S was given for all kappa negative using, again, replicas by Franz and Paris in 2016. Hamed El Alaoui and Mark Selke used an, developed an AMP algorithm that under some assumption constructs solutions up to some points. And, I will not go in technicality. And then there is a result of Baldi and Vershinin that gives a bound on the radius of this polytope that I described before. And this is tight within constants. And, okay. So here I state the result where the xi are random, and yi is related to the xi by a general link function, and I assume that the link function is logistic-like. So at infinity goes to 1, at minus infinity goes to 0, and it goes, the approaches are, exponential with exponent alpha. So alpha is a little bit a measure of the SNR. Okay, so for this model, we can characterize basically what is the threshold for large kappa, large negative kappa, and this goes like e to the alpha kappa log kappa divided by 4 phi kappa, where phi kappa, capital phi x, is just the Gaussian CDF. Okay, so what is the intuition here? Well, the simplest thing to understand is the leading factor is really this phi kappa that is like e to the minus kappa square. Why phi kappa delta appears here? Well, this is phi kappa times n over d. And if you think about it, phi kappa is basically the relative, the fraction of volume that is cut by each, the volume of each. I described this set of minimizer as a Gruyere cheese, and phi kappa is really the volume of each hole of the Gruyere. So each time you cut a sphere with an hyperplane, you cut a piece of relative volume phi kappa. So n times phi kappa is the expected volume that you cut out with this hyperplane. And you want this to be proportional to dimension. Okay, so this for large kappa nails the threshold, but it doesn't even establish that there is a sharp threshold at any kappa. So in a sense, okay, it's a reasonable result, but there is a lot more to be done. And this is the picture as a function of kappa, the scale thing. Okay, we can obtain the same result for pure noise. And here I plot the lower bound. So we have an explicit lower bound and explicit upper bound, and I stated before the asymptotics. And I plot also this replica symmetric result. So this is physics language, but this was proved, is an upper bound proved by Stojnic in 2013. In fact, Stojnic also had a formula for this upper bound, but the better upper bound, but didn't derive the asymptotics. In the pure noise case, the formula. Okay, now there is another line here, is what we can probably achieve with any algorithm. This is what we call delta lin. So, as I said, finding an empirical risk minimizer in this case is a non-convex optimization problem. And okay, so we came up with the convex heuristics that can solve the problem up to this point for any delta less than delta mean. And as you see, there is a significant gap between the two. And in fact, here I state, the result with delta lin. So delta lin, doesn't have, is below the satisfiability threshold by factor log kappa over 2. Okay, so the best polynomial time algorithm we know that achieves a threshold above this linear programming threshold, but we don't have at the moment upper bounds on this. But something very interesting is happening here that was not happening before, was not happening in the convex case, of course. There is a large range of values of the overparameterization ratio, such that any n over d between delta lin and delta s, in which we know that there exist empirical risk minimizers, but we don't know how to find them in polynomial time. Okay, so in this case, this is as far as I can see, as toyish as it is the only case that I know in which I can say, yeah, overparameterization probably helps. Now, I don't have an upper bound of delta alg, so it could be that there are better polynomial time algorithms than this linear programming algorithm, but okay, I suspect no. But at least the analysis of this linear programming algorithm is tight, so at least for that class of algorithm, there is a gap. Okay, so in this case, we can have a characterization of the threshold, and we can say that overparameterization helps. So okay, just one word about what are the proof techniques, because I said the proof technique in the convex case don't really apply here. So the upper bound is based again on a Gaussian comparison inequality. The key thing is that, the interesting thing is that instead of applying it to expectation of the, I should have written not loss, but risk. So normally one applies Gaussian comparison inequality to the expectation of the mean of r theta. Here we apply it to the expectation of the exponential of, oh, this is not theta, this should be a lambda, another. You apply the Gordon inequality to the moment generating function, and optimizing over this lambda, you can obtain a vast improvement over the naive bound. So this is this big improvement. It really changes the order of the transition, which I find really remarkable, actually. And so this, we discovered this idea that actually Kanje discovered these ideas, and then we realized that in the Storchnich, one of Storchnich's paper had this same idea. And then the lower bound, you do a second moment method. So a lower bound, you want to prove that there are minimizers. So we define something that is, okay, naive, you would like to define something, a random variable that is the volume of the set of minimizer, and prove that this is strictly positive. Okay, so you compute easy square, and then you do Palais-Zygmunt inequality to prove that this is positive with positive probability, show that this is basically the square of that, and then you do Palais-Zygmunt. This doesn't work. The volume is not the right quantity to work with, but there is an integral over solution that works, a weighted integral over solution that works. Okay, so this is so far for this simple model. Now what this upper bound and lower bound, now I went quickly over it, but is probably 40 pages of proof. And what we really want to get at is this, at least 2 layers neural network that looks, dauntingly more complicated. Okay, so I want to ask which techniques do we want to use there? And okay, I'll argue that projection pursuit is an interesting point of view. So let me take a detour and describe what is projection pursuit. You have data in d dimension, x1 to xn, point in data dimension, and we want to visualize them. Initially, this was the motivation, by plotting projections, m-dimensional projections. And of course, the interesting case was m equal 1 and 2. So Friedman and Tukey, Jerry Friedman and John Tukey came up with it in 1974, and it's beautifully short abstract. So the algorithm seeks to find 1- and 2-dimensional linear projection of multivariate data that are relatively highly revealing. It's nice to be able to write such a short abstract. And this was their one of their data example in which they had particle physics data in 7 dimensions, 500 data points. And here they try to find informative dimensions. So these are the naive low-dimensional projection that are obtained by principal component analysis. They argue that they are not very informative, and these are by their method, and they argue that they are very informative. And in fact, they have some structure. Okay, very nice paper. 10 years later, Diaconis and Friedman came up with some theory for it, and for large N and D. And in particular, they came up with a null model that I'll describe in a slightly different language. So they said, let's say that we have, one section of their paper says, let's say that we have data that are I at D normal 0I. So they have no structure. I mean, the question they wanted to ask is, okay, by seeking spatial direction, you find very strange distributions, right? Non-Gaussian distribution. But perhaps this is just a consequence of the fact that there are many dimensions. And so by looking hard enough, you will find every possible distribution. Okay, so they said, let's look at this model. Let's assume that the data I at D normal 0I, n and d goes to infinity, and n over d goes to delta as before. And then I say that the distribution in Rm is feasible if there exists a sequence of orthogonal matrices, so a sequence of projection, such that what happens, if I look at projection of the data points in those m dimensions, so these are d by m, so they are projection to m dimension. If you look at the projection in m dimension, and I look at the empirical distribution, so the distribution that puts mass 1 over n over in each of these projected points, this converges weakly as n and d go to infinity to p. So this is what it means for p to be feasible or asymptotically feasible. These are the projection that you will be able to see as low dimensional projection for large n and d. And I'll call the set of feasible distribution calligraphic F. Does this make sense? Okay, I hope that the definition makes sense. This is a subset of the set of probability distributions in m dimensions. So what is the connection? Let me give you a preview of the connection. If you think of a 2 layers neural network with m nodes in the hidden layer and d nodes in the input, and I fit n data points, it's important to know what is the possible value that you observe here, where W run over all possible matrices of weights here. Okay, so W here, the set of weights, is really a matrix that is D by M. And I let it go over all possible matrices that are D by M. Of course, doesn't matter that the matrices are constrained to be orthogonal or not. And then I want to see what is the set of empirical distribution that I see here. Okay, so this is clearly important to understand, right? In particular, think, for instance, back at the negative perceptron case. what does it mean that you achieve interpolation in the limit? So this is an asymptotic meaning. It means that all of these yi, theta, xi, that there exists a theta such that most of yi, theta, xi are bigger than kappa. Now, if it is pure noise, you can rename yi, xi, xi, and you don't change distribution. So you want that when you project along theta, that is a one-dimensional vector, all the projections of the data point must be to the right of kappa. But what does this mean in my previous language? It means that there exists a P that is a one-dimensional distribution that is feasible and that is supporting kappa theta. So if I can understand what is the set of feasible distributions, I can tell what is the interpolation threshold. The same is true for small two-layer neural networks, right? So take a two-layer neural network is something like this. Without loss of generality, I can take W orthogonal. And okay, I can take H to be many different cases. It doesn't matter. For instance, I can take H to be a generic Lipschitz function, to be a two-layer neural network in which there are, or to be something more complicated. Doesn't really matter. It's a class of things. And now I ask myself, when I can achieve interpolation in this model by letting H running over any function. Okay, first of all, you can, for simplicity, let's assume the pure noise model and H odd. You can push the Y inside because H is odd. So you get this. And this happens if and only if. So you achieve interpolation, there exists a P that is feasible, an m-dimensional distribution that is feasible at overparameterization delta, such that P is supported over H of Z bigger than kappa. Okay? So again, it's a question about optimization in this space. Okay, so if you know that thing, and it cannot be really made simpler than that. Right? I mean, in the sense that if you don't solve this optimization problem, you cannot solve the original problem, right? And I must say that something related representation. So this interpolation problem was studied again in physics by Franz Wang and Urbani, and they have a similar representation to this. Okay, but okay, so this representation is kind of an easy fact. Okay, but summarizing what we know, what we said, we say that interpolation for a model in RD, so in a high dimensional, is equivalent to optimization over a certain set of probability distribution in a low dimensional space, as long as the neural network is small. Okay, so characterizing this set of empirical risk minimizer, that is a complex thing, boils down to characterizing really this set of probability distribution. So this is what we set out to do. And okay, this is what I wanted to report on. Okay, for stating the result, it's convenient to say, make one remark and one notation. Obviously, the Gaussian distribution is always for any delta inside this set. Why? Because if I take Gaussian data in one dimension and I fix a fixed, a given m-dimensional plane, say the plane spanned by the first m coordinates, that projection is obviously the empirical, the projected points are Gaussian because you are projecting to a fixed subspace, and the empirical distribution of IID Gaussian point converges to Gaussian by Glivenko-Cantelli, if you want. Okay, so this point, so you can think of the space of probability distribution in RM, the space of feasible probability distribution at level delta, and then the normal distribution, in a sense, is the center of this space. And as I add more and more constraints, more and more points, as delta gets larger and larger, this set will of course become smaller and smaller. Okay, so for characterizing f, I will introduce this notation. I'll call BRT0 the ball. If I put a subscript here, the same subscript here, in the distance d in the space of probability distribution with center P0, and typically I look at the center to be the Gaussian probability distribution. Right, so what was known before in the last, since 74 is 48 years. Diaconis and Friedman proved that for the one time m equal 1 and delta large, the set of feasible distribution is inside the Kolmogorov-Smirnov ball with the radius that goes to 0 with delta. And then there was a paper a couple of years ago, or 4 years ago, by Bickel, Kur, and Nadler that proved that this bound can be upper bounded. I focus on delta bigger than 1 because it's the most interesting. Is upper bounded by basically log delta, square root of log delta over delta. Okay, so these are the available results. So now I state the new result. Okay, first result number 1, for m equal 1, there is a very nice exact result that can be proved that is we can compute the exact W2 radius of this set. And W2 means Wasserstein 2. And it is 1 over square root of delta. Bickel et al. Also had the result of this for delta less than 1, but it's not tight. And so this is the exact radius. So this set is inside a ball of radius 1 over square root of delta in the Wasserstein metric, and actually basically touches the boundary of this ball for any delta. Unfortunately, this works only for m equal to 1. For m bigger or equal than 2, we get a kind of up to constant bound for the Wasserstein radius is basically square root of m times log delta divided by delta. Now, the square root of m must be there, but log delta is probably spurious. Now, I claim that this W2 of Kolmogorov-Smirnov bounds are not the right, okay, they're okay, but they don't capture everything. And to understand why, let's look at the following distribution. Take a quantized normal distribution. What I mean by this, I take a Gaussian distribution in m dimension, and then I look at the law of the vector g when I quantize at level epsilon. So this is a discrete distribution. It's supported on epsilon times ZD. And of course, when epsilon goes to 0, its distance from the normal goes to 0, both in Ks and in W2. And so according to the previous bound, for any delta, you can take epsilon small enough so that this distribution is feasible, which would be very strange, right? It would mean that you take Gaussian points in d dimension, you project in 1 dimension, and you get a discrete distribution. And in fact, it is false if delta is bigger than 1. I mean, you can achieve it trivially for delta less than 1, but for delta smaller than 1, no? So from this, we deduce that these W2 and Ks distance do not capture really the structure of F. And okay, we have a more general result, I think that, okay, I'll state it here perhaps. Okay, it's a theorem, but let me write it here. It's an upper bound that unifies modulo logs, all the previous one, more or less. And it says the following: if P is feasible, then there exists another distribution Q that is close in W2 distance to P and is not too far in Kullback-Leibler divergence from N. And this implies basically modulo logs all the previous upper bound that I stated, and the paper contains a related inner bound. So In a sense, I think this is the right bound. Okay, so we have a bunch of results on this. What I want to come to now is so this per se, I think it's a very interesting problem, right? It's a very kind of a universal high-dimensional statistics problem, because basically all high-dimensional statistical problem can be phrased in terms of this. And so now I want to come back to neural networks and describe the version of this problem. So far, I always talked about this pure noise model. What happens if there is a signal? So one can introduce a supervised version of projection pursuit. So I want to describe this and a couple of consequences of this. So what is the supervised version? Now, instead of having, as in the Diaconis-Friedman paper, IID Gaussian vector, you have both feature vector and labels. And the labels are distributed according to a link function times a low-dimensional projection of the data. So K of order 1, and this is an orthogonal matrix. And I'll take n and d go to infinity with both m and k fixed. And now, as in my definition before, I defined a distribution on plus or minus 1 times Rm feasible if there exists W such that the joint empirical distribution of the yi and the projection of the xi converges to P. And now we have a new set that depends on this link function phi. The previous case was the case basically in which phi is the constant 1/2. And this is a new set of feasible probability distribution, and we can apply to it all the tools that I described before. I don't want to go over that. So what is the program here, which I think we are just scratching in the beginning, is characterize the set, deduce bounds on the interpolation threshold, and then characterize the subset that is reachable by efficient algorithms, etc. So I'll give one example, perhaps, of this. I don't know, 2 examples. So I have 2 examples, one very simple, one more complicated. I'll give you the very simple example because I can go. And the very simple example is this one. Max margin classification with kappa positive. So this is extremely simple, but just to show that this approach can derive tight result for, I think it's always nice when you come up with a nice idea that you recover all the results from a new point of view. So in this case, as I said before, if P is feasible in 1 dimension, then it must be that the W2 distance between P and the normal is less than 1/square root of delta. And plus the max margin condition, the margin condition implies this. So in this limit means that the support, this P is really the distribution of the 1-dimensional projection. It must mean that the support of P is in kappa infinity. So when are these 2 constraints satisfied, can be satisfied together, right? We want to solve the problem of minimizing the W2 distance between P and the normal, subject to the support of P being in kappa infinity. And now it's clear what you have to do to solve this problem. You take the normal, you truncate at kappa, and you put a delta mass at kappa that is equal to all the area here. Okay, so this is the solution of this problem, and this is the minimum value that it can achieve is the W2 between kappa and normal. So you take the normal, and then you have to move all this mass here, there. What is the transportation cost is kappa minus G positive part. Okay, so the fact that the bound on the transportation ratio, so this has to be smaller than 1/delta. And so this means that the interpolation threshold must be less than this value. I think it's -1/2, sorry. Okay, so this is tight. So we derived an upper bound by quite different point of view from what we used before, was used before. For instance, in our paper, I mean, this is actually Srebina-Tirozzi and Stojnic paper. This is to some extent a different point of view. And we obtain a tight bound, and we obtain as a corollary also an interesting fact that the distribution of the margins is asymptotically given by this one, right? Because if it is tight, it must saturate the upper bound. Okay, we can apply the same logic to, you know,
Andrea, I think we have about four or 5 minutes left, which was supposed to include questions. So
sorry.
If you want to, no problem.
I'm done. So as I said, I'll skip the other example that has to do with neural network, and I'll just mention that, okay, understanding this set of empirical risk minimizer is difficult because this set is very high dimensional. So you want to look at it as a functional number of dimensions. But for small neural networks, the geometry of this set can be encoded in the geometry of this set of probability distributions, which I think it's very interesting. And so you can really, any property of this set of feasible distribution translates in a property of ERM naught. And okay, as a side thing, we had a generalization and proved the new results on projection pursuits. That's all.
All right, we should give a round of applause. Really interesting talk. I don't quite know whether we just take questions from the attendees through the chat and or panelists. I guess we'll just do it all at once. So if anybody has any questions, feel free to just unmute yourself if you're able to do that and ask, or you can put a question in the chat or the Q&A. So I'll get us going with a question. One of your earliest pictures in the talk had a picture of the set of ERM minimizers, right? And it looked, you do this by hand, it looked very, very non-convex, which was suggestive that we were to expect, you know, some ugly non-convexity to come later in the talk. And then you showed for the, yeah, if you just focus on the picture, that's fine, even or wherever you'd like to go. But I think you know the picture I mean. Yeah, okay. And this one, yeah. And then you showed us that for the kappa negative case, which you called negative perceptron, that what you ended up getting was the set difference between the sphere and a bunch of spherical caps that you take out. So it's like a ball with holes. What is your intuition about what this set would look like for, let's say, a somewhat realistic neural network architecture? I don't know if your intuition carries from the negative perceptron, but like, let's say, imagine we just tried to approximate this empirically with a ton of ridiculous, wasteful computation on some neural network architecture that we ran for a very long time. We ran, like, you know, optimization for a very long time. Like, I know that's not feasible to do empirically, but let's suppose we tried to do it. What would you expect it to look like?
Well, I expect it to be horribly non-convex. I think that we even know that it's horribly non-convex. I don't expect to be simpler in any way that the negative perceptron, right? And I expect in general not to be able to find a point even, you know, unless the problem is very overparameterized. Probably there is no polynomial algorithm, you know, close to the threshold in which it becomes overparameterized. We'd expect that there is no polynomial algorithm. But now the question is that, you know, I don't think it even, you know, how do you think of the L1 ball? I mean, in high dimension, it's very difficult to come up with a picture, right? And, you know, I cannot think of a simpler convex set than the L1 ball, right? Basically, and it's very difficult. It has a lot of counterintuitive properties, right? So as often is the case when you want to think of a a high dimensional set, you want to think about low dimensional features of this set, right? Or what do you think the high probability set? Say that I give you even a simpler example, because then the high dimensional. Say that I give you a IID random variables that are Laplace distributed, right? What is the set of high probability of this? The typical configuration. It's very difficult to come up with the set of entropy, whose empirical entropy is close to the set of typical set in information theory sense. It's very difficult to come up with but for instance, that is exchangeable and its empirical distribution is close to the actual distribution. So this helps you think about it, right? And the same DL1 ball is uniform given the empirical distribution, a typical point there. And I think here what we are trying to do is the same. I think that as the way to think of a point of L1 ball, a typical point of L1 ball, the right way to think about it is basically an IID sequence with some distribution, some empirical distribution. Basically the same that is what we are trying to do here. Instead of thinking directly of ERM, you should think about, at least, first of all, how it looks like depends on the question that you ask, of course. And I say that if you are looking at, if the question that you ask is fitting a small neural network or any model with a small number of hidden units, the right way to think about this set is really through this feasible set. That itself is not an obvious object, but at least is an object in finite dimension. It's a set of probability distribution whose dimension is not going to infinity.
Very interesting. I'll follow up with a question/comment later. We have another question in the Q&A. Andrea, I think it would be best if you just answered it directly, if you know how to do that. Let's thank Andrea again for a great talk. Thanks.